right, good afternoon. I'm Hatori from Preferred Networks. So today I'm going to present about interactively picking real-world objects with unconstrained spoken language instructions. So in this work, we're going to focus on the task of human-robot interaction with spoken language. Such natural and unconstrained spoken language is one of the most intuitive and versatile ways of communication. As a robot expands their workspace, there's an increasing need for a robotic system to which you can talk to using your everyday natural speech. In this context, there have been several nice works in the past, but most of them have either focused on limited vocabulary or grammar, or kind of focused on the subtask, simplified task. So in this sense, we haven't actually explored the full challenges and complexity with the real-world spoken language. So why is it so difficult? We believe there are two reasons. First, there's a huge variety of spoken expressions referring to the same thing. Like, for example, how you want to point to the bear on the top right corner. You might say teddy bear, brown plushie, or that fluffy thing. Or someone could say upside down doll in the upper box, like this. And if we also consider the variety of the sentence structure or phrasing, there are much more diversity. Can you grab X, or could you move it, or put together X and Y? And secondly, what we say, human instructions, are quite often ambiguous or even erroneous. If you just say, grab me the brown thing, there are actually many brown things in this picture, so the instruction is ambiguous. Or you might just mistaken the bear for a dog, and you could say, pass me that dog, but we kind of get it, even though it is wrong. So our work is an attempt to tackle these two challenges and trying to work on a realistic system on this kind of task. We're going to speak to the robot using very natural speech and asking it to pick one specific object and move it to another box. It goes like this. Hey, can you move brown fluffy thing to the bottom right? And if there is one object matching, the robot is going to just execute the task. If it's not, in this example, it's going to ask you back, oh, which one do you mean? While highlighting all the objects matching what you said. Then you could add some additional clarification. Oh, I meant the one next to the eraser box. And he gets it. All right? So seeing is believing. So let me play a video of the system that we have actually developed.
Can you move the brown fluffy thing to the bottom?
So she's using a kind of vague expression.
Sure, I'll work on that.
Fluffy or brown. But we are doing a real-time matching from the what you said and what you are seeing from visual features.
Can you move the tissue box to the left?
And of course, you can understand specific nouns like tissue box. And the video is a real time, so real speed, by the way.
Can you move the white and blue box to the right?
So instead of saying tissue box, you
Sure,
could say
I'll work on that.
white and blue, like referring to the colors, texture, size, and positions of the objects, for example.
Can you move the orange triangle thing to the top left?
Yeah, like this example. You don't know the actual
Sure,
name,
I'll
what
work on
it's
that.
called, but it's orange in triangle. And still, we can do the real-time matching from the visual feature and your speech.
Can you move the sandal to the top right?
She's asking for sandal. You actually have two sandals.
Sorry, which one do you mean?
The red one.
Sure, I'll work on that.
So in this kind of example, there's ambiguity in the given instruction. So there is the interactive clarification process involved, and the robot is not going to execute the task until the ambiguity is resolved. Okay, so how we did it. Our system It is fully based on the neural network structure. And the important thing here is we didn't hardcode any kind of vocabulary or the phrase or grammar structure. The robot doesn't know the meaning of any single word until it is given the data and trained in the end-to-end fashion. First, we are given a vision RGB image. Then we apply SSD, which identifies bounding boxes for each object. Then we can crop the images for each object. And each of these images are processed by CNN to extract visual features. We also have the textual input. This is a transcribed speech text. And it is first converted into vector representation in the embedding layer, and then processed by LSTM to extract feature vector from the text. And finally, we do the comparison of the visual and textual feature vectors and outputs a target object as the highest similarity score. There is also a separate path to predict destination box, but this one is based on the same neural network architecture. Okay, and how we handle the ambiguous cases. So we train the model with a hinge loss for the positive and negative object sentence pairs. Given this kind of text instructions and this kind of image, there might be several competing objects for a given instruction. So in this case, there are two brown fluffy things. And each of these objects are fed into the neural networks, and we're going to calculate the score for all the items. And the hinge loss kind of ensures that there is always a certain margin between the best and non-best candidates. And trained in this way, at runtime, the system is able to consider all the candidates as ambiguous if the margin is below threshold. Okay. And because we are kind of defining a new task and we want to train the neural network in an end-to-end fashion, we have created a new data set. We first picked 100 types of common objects as you find at home. And by randomly picking 10 to 30 objects, we just scatter them around the boxes and take the image. And we have collected 1,200 scenes in total. And for every object in every scene, we annotated at least 3 text instructions referring to how you're gonna say if you want a robot to move it. And this is based, we use the crowdsourcing for this annotation. And the important thing here is we didn't tell the annotator to use any specific phrasing or use simple vocabulary. We just told them to annotate what you're gonna say if you're talking to your friend or family. So therefore, it is a collection of very natural and unconstrained text instructions. And this data set is publicly available, so you're welcome to give it a try if you're interested in. Okay, finally, I'm showing just one result here because we don't have much time today. So here's the accuracy of the target object detection. When a single instruction is given, our system has achieved 88% accuracy. And by incorporating interactive clarification step for the ambiguous cases, we could further improve the accuracy by 4.7%, reducing the error by 39%. Okay, so in summary, we proposed an interactive picking system to which you can talk to and control using natural, unconstrained spoken language. On this realistic and challenged data set, we achieved an object detection accuracy of 92.7%. And we have shown that interactive clarification step is indeed effective for the ambiguous instructions. And last but not least, I'd like to show some of the future work in progress. So we are working hard to extend the model to support more objects, more messy environment, and more language. We have about 17 objects here squeezed,
右下の箱にある輪ゴムの箱を上に動かしてください。
and it's actually in Japanese.
わかりました。
But the system is still working accurately and in a robust way.
左上のマスタードのボトルを右下に。
わかりました。
Okay, so here is the latest status of the system. Thank you very much, and I'd be happy to take questions.
Any questions? Just raise your hand. Any questions?
Thank you. Quick question. Who were the participants who were instructing the robot on how to behave? Were they researchers or were they the general populace?
Sorry, can you repeat that question?
When somebody was telling the robot, move the tissue box down to the bottom left,
Yeah.
were they researchers?
Oh, okay, so for this accuracy that I showed, that is the, based on the data or the crowdsource. So that means that normal people, no researchers or engineers.
Awesome.
Yeah.